it's a very energy-consuming separation system. Because the separation factor 1 means theoretically impossible to separate. Only small difference, 1.05, 1.2, even in the current system is 1.2. So we need to develop more about this mechanism, or discover this mechanism. So this is a big issue. So we synthesize this type of porous structure, big pore and the small channels, big pore, small channel. On the small channel, we put this type of the local motion ligand. So the motion is just like a dragonfly. So using this channeling system, we try to separate these materials. So this is the this is the results, and the H2O diffuse much faster than the heavy water in our system. But usual zeolites, activated carbon, HKUST1 MOF, GIF7 MOF, and the other MOF materials show the exact same diffusion. So we succeeded in this kind of the discrimination of these materials, the separation factor up to 200 at room temperature. So this kind of flexibility, the dynamics is very important for the very difficult tasks. So at the moment, and very recently, we had a big sort of the question, because in 1997, this is very important, our materials. We carried out first demonstrated gas absorption, but without gas here, this structure, the pore size is smaller than the gas molecule here, for instance. How gas molecule accommodated in this way? This is a big issue. So we revisited these materials, and this case is the CO2. CO2 absorbed at the lower pressure region and smoothly absorbed. And what is interesting in the second, this pressure abrupt adsorption occurs here. So we determine the crystal structure. We can see the adsorbed CO2 molecules. Why this happens? So the result, two distinct behavior coexist. That is local flexibility and the phase transition, global dynamics. In particular, in the local flexibility, and this is the narrow channel. So narrow channel aperture like this. This is constructed from the bipyridine and the nitrate gate. So bipyridine rotate like this. So therefore, this gas molecule can diffuse easily. We call this is pore squeezing diffusion. So conclusion is, our compound at 1997, born to be soft. Very interesting. Already I found, but I did not know that. So, summarize here, each university initiated the development of porous materials based on this concept. So now realize, when I was a graduate student, I thought this kind of notions. So, and here, at the beginning, I showed you this kind of the functionalities. So many researchers discovered this kind of functionality, the storage, capture, and also the separation and the synthesis on the polymer and the catalysis, and also the physical properties in the ion conductivity, in the magnetic properties, and also the optical properties, and also the different type of absorption profile. So this is very fantastic, but still the application we can expect. So from the the robust framework and the flexible framework. In addition, these frameworks, we are now developing this type of the hybrid MOF system, using the other materials. So this is very important for the practical use. So the keyword in the assembly, space, dynamicity. These are very, very important for in the keywords in the porous materials, in particular in the MOF materials. So we can expect the expanding this functionality more and more, and also the commercialization that just started. And the good news is still now we have more than 55 startups in the world. So these startups contribute to the scale-up production and also the low cost MOF materials. So I am the fundamental scientist. I handle only less than 1 gram materials. So for the commercialization and the transfer to the society, we need to have kilogram or ton scale materials. So it's a good teamwork from fundamental and the startups and also the society. So this is very nice, the case. Okay, so at the beginning, I told you the gas materials widely distributed and the closely related to the various aspects in the environment, energy, and also in the our body control. So, even so, we need to develop new society, new world, depending on the ubiquitous materials. So, in a sense, if we can use air, so we can say the gas age is from real gold. Real gold is just gold. Right now, the price is high. All the people are interested in that. It's too short range. But the black gold is coal and the petroleum. And now it's air gold, or future air gold. We need to use air. So even in the small countries, air is equally distributed. That's very important for our future. So, and I'll say in the Chant2, at the beginning, I told you about the usefulness, useless. But he also said here, and the living by use of mist. So, what is mist? So, mist is contains the air and the water, contains everything. So, 2,400 years ago, he thought something about this, but that time it's not just a dream. But now, it's not dream, in particular in the future. So we are standing in the future, toward the future. The air gold and the porous materials, of course, in the not only the MOFs and the related MOF materials and porous materials, I mean, porous materials make our dreams come true. That's very, very important for the future. Okay, so this is my academic network. So prepared by my collaborator and the Minshu Yao, and so maybe it's difficult to see the name, but later on, please look at this. So this journey was never mine alone. It was worked together by collaborators, postdocs, students, funding agencies, institutions, and my family. My deepest thanks to all of you. Thank you very much.
Thank you very much, Professor Kitagawa, for that very dynamic and very useful presentation. Thank you so much. It's time for our last but not least speaker, Professor Omar Yaghi. And Professor Yaghi was born in 1965 in Amman in Jordan. And after a while, he went across the Atlantic, and in 1990, he was awarded a PhD degree from the University of Illinois at Urbana-Champaign, or UIUC, in the USA. After that, he moved around a little bit in the US, and finally ended up at the University of California at Berkeley, where he is now active. So by that, please join me and invite Dr. Yaghi for the stage.
Thank you. Okay, thank you, Olaf, for the introduction. And I also want to thank the Swedish Academy of Sciences and the Nobel Foundation for bestowing this honor on us. And it's a tremendous honor, and I want to thank all of you for being here. I want to share with you the journey that MOFs have realized, and that is a journey of molecules to society. It is not very often that chemists can move from molecules to society, but metal organic frameworks, fortunately, we have been successful in plotting this path and following this path. What are the key developments along this way, the key discoveries that made the field what it is today? That's really the subject of the first half of my presentation. And the second half is, what does the future hold? At least some of the future. I was fortunate to have a student, her name is Guanming Li. When I first arrived to assume my independent position at Arizona State University back in the 1992, that she insisted that she wants to work in my group. And I haven't even opened the boxes. And I discouraged her from joining my group because I thought she could do better with a more established professor and can publish much more quickly. But she insisted, and I kept pushing her away and coming back. And I will return to Guanming, but she started working with these things, metal organics, just like the ones you have been listening to for the last hour. Copper-1, that figured prominently in both Richard Robson's talk and Susumu Kitagawa. And this bipyridine linker, it's a neutral linker. That's a key word that I want you to remember. And again, she made this, showed it to me, and I said to her, I don't want you to work on these things. They are not very useful, okay? And remember, I was a young professor trying to make tenure. So I wanted to make sure that I do something new and useful. So the reason I discouraged her, needless to say, she didn't listen to me, which was in the end, it worked out well. The reason I said I'm not interested in this is because it's already been done back in 1959. People have used copper-1 with adiponitrile to make metal organic, what they called coordination networks, or not yet coordination polymers, but coordination networks. And you can see this is a diamond-like network, right? And This was already mentioned by Susumu, that a German report showed very similar strategy with copper-1 and this roughly, let's say, linear linker to make the same kind of network. And when I was a graduate student, I saw this report when it came out by Richard Robson. Again, exactly the same kind of network, made in the same way, same metal ion, and the linker is a neutral linker. In this case, a tetracyano linker, as Richard described. But in Richard's paper, I thought it was very interesting to me as a graduate student that he started talking about how one could expand the linker. You can make a longer linker, perhaps. Perhaps you could use other metal ions. And as a graduate student, I found that variability to be very refreshing, because people who worked on materials, this type of control was not possible. So those ideas put forward by Richard Robson and later acted upon by Richard Robson were very nice. But there is nothing new under the sun, because there were previous reports that they were not too dissimilar from what Robson did. But his paper, which I encourage all of you to read, in 1989, outlined some ideas that at least a graduate student such as myself found interesting. So back to Guanming and her coordination network, is that they were beautiful but frail. That was the problem with the coordination networks that preceded what we call MOFs. And beautiful is great because I love beautiful objects. And in fact, I went into chemistry because of the beauty of molecules. Then we came across the report by Susumu Kitagawa with another coordination network. And there Susumu showed that he could, under pressure, have gases permeate through the structure. Under high pressure, as he just described. So there were two reports here that for me as a young graduate student and a young professor sort of opened my eyes to this area. And I want to give tribute to my PhD advisor who taught me that science begins with doubt and questions. And that is so true. And that I was taught in graduate school, and I started acting upon it at this stage of my career. So the report by Susumu raised, in my mind, two important questions. One, are the pores homogeneous in size and shape? Pressurizing compounds does not give you, under high pressure, studying gas adsorption under high pressure, it does not give you this answer. Okay, so that was a question we needed to answer. And then we also had to answer this question: do the pores remain open in the absence of any molecular guests? Those are two very, very important questions. The first question is saying, do I have a system that has homogeneously sized and shaped pores so that I can selectively remove molecules that would fit in those pores? If you have a different wide distribution of pore sizes, then it would not be selective. So that was an important question. And the other question is, can they remain open, like this architecture? When we leave this room, the architecture doesn't collapse because it's robust. And so those two questions needed to be answered. And so far, no experiments were done to answer those questions. So my approach was, the obvious thing to do is to say, instead of those frail frameworks that are made from weak bonds, make them from strong bonds. Okay, so we started thinking about how do you make strong bonds between transition metal ions and organic linkers? Well, instead of neutral linkers, you use charged linkers, because the extra charge on the linker increases the strength almost 3 times. So the bonds that I'm talking about, as you'll see shortly, are charged linkers, and when they are bonded to metal ions, they are worth 3 times the energy that the bonds that were made in the earlier examples I've given. Okay, well, that sounds easy enough. But when you have strong bonds, something very bad happens in the lab. And that is, you make ill-defined materials, not like those beautiful crystals that were described earlier. This hump indicates that your material is completely disordered. The homogeneous pores that I was talking about, if they're present, they wouldn't be homogeneous. The framework that I was talking about that should be robust, it wouldn't be. This thing is a complete mess, and it's the antithesis of what a chemist want to do. So at that time, it was taken as an article of faith that our approach could not produce crystallized materials. We could not make crystals. So the very first thing that we needed to solve before we get to the architectures, robust architecture, we need to be able to make them in crystalline form so that we can characterize them fully on the atomic and molecular level. If we can't do that, then you can't learn anything about what you're doing. So now we come to my postdoctoral advisor who taught me science is an exercise in optimism. So now we are facing three major problems. We need robust architectures, we need homogeneous pores, we need to crystallize the material. None of that has been done thus far, and we needed to be optimistic so that when we do the experiments and we fail, we can at least do more than one experiment and try as much as we can to make it succeed. And that brings me to this lady, Marie Curie, and her eyes. Let's focus on her eyes. This portrait sits in my conference room, and every once in a while when things are tough, I ask the students, what do you think she's telling you with her eyes? Okay, and I think inevitably, she's probably saying to you, you can do more and you can do better. And this turns out to be a very important motto in my group, is that I think we can always, every one of us can do more and can do better. So, okay, so let's get down to what is the challenge that we needed to solve first and foremost, and that's the crystallization challenge. The crystallization challenge is a challenge where you're taking building blocks and you're stitching them together now through strong bonds, and you need to make sure that on the microscopic level that these building blocks can associate and dissociate so that they can correct their positions and make sure that you make an ordered material. If this reversibility is not present, then things will get stuck together and sometimes not at the proper orientation, and they will fall out as amorphous materials or non-crystalline. So that's one thing you needed to ensure, that things can be bonded and broken on the microscopic level until they are fixed in position so that they are ordered. The second important thing is that this process of coming together and separating needed to be at the right speed. If it's too slow, then you don't make large enough crystals. Okay, you make fragments. And if it's too fast, then you make that awful hump I was talking about, this amorphous, ill-defined material. So that was the challenge that Guanming solved. She found the recipe that would take, for the first time, a charged linker, such as carboxylate, with cobalt-2+ to crystallize the very first MOF. Okay, so that was a big success made by Guanming Li. Guanming Li, remember, is the young student that came to me and I pushed her away. Now she is successful, and 20 years later she came to visit me. And I was very saddened when she said that the reason she insisted on joining my group was that nobody else would take her. Okay, so, but she opened the door to this amazing field. And then Halian came in and developed a recipe that would always give you crystals, okay, most of the time, let's say. If you were working with carboxylate and transition metals, you use this recipe and or a slight modification of this to make crystals. And here you can see he made well-known junctions, like this paddle wheel, well-known in inorganic chemistry, but now it's linked by organic. The reason this is a magic recipe is that this amine, he was very clever in that he did a very classic crystallization where he diluted the amine in toluene, set it outside the solution, and then because it was dilute, it slowly diffused in, and this slow diffusion deprotonates the acid and starts the reaction with zinc. You have more control over this chemistry. Okay, so here is the first MOF that showed some openness, and now you have DMF molecules that are trapped inside. Okay, so the big question was, could we take these DMF molecules out, and if we do that, will the structure remain open or will it collapse? The nice thing about the carboxyl is that not only do they give you strong bonds, but they chelate, they grab onto, they claw onto the metal ions and assemble them into clusters. So we were very optimistic that this would have that permanent porosity. And so that's where Mohammed Adaudi joins my group. The way I met Mohammed Adaudi is that I was supposed to give a talk in Lyon, France, and I overslept and missed my talk. And they all were very worried about me and sent Mohammed, who was studying in France, to pick me up to find out what happened to me. And he asked me on the way to the conference, he asked me for a postdoc position. I was delighted. One of the best decisions I've ever made is to ask Mohammed to join my group. And Mohammed's task was to do what everybody understood, especially in the zeolite field, that the gold standard for determining permanent microporosity was to measure a gas adsorption isotherm, and it has to be done at 77 Kelvin and low pressure, so that things can diffuse spontaneously into the pores. And he did that experiment. That's the first time that a gas adsorption isotherm was measured for MOFs, and it was absolutely decisive. The shape, first of all, the shape is a knee shape. That's a type 1 isotherm, and the theory of sorption tells you this material is permanently open. And you can get information such as the surface area from this data, and the surface area was 275 meters squared per, disappointingly low. But this experiment showed beyond doubt that you have permanent porosity. And then the zeolite chemists can now talk to us, the traditional porous material crowd, the zeolite chemists who've been after us for years because we didn't have this experiment. Finally, now we can compare MOFs to zeolite, to the more established materials, and MOFs joined the club of porous materials. I was able to find the faxed reviews on that paper, and I was very pleased with these reviews. I don't think I get reviews like this anymore. But this manuscript should be of wide appeal to a general audience interested in the synthesis and use of metal organic porous materials. Invariably, the porosities are generated by removal of solvents and organic groups or by topotactic structural rearrangement. Until now, the major limitation of these materials has been in the ability to create systems with the necessary structural stability through low temperature assembly techniques. This work is a benchmark for solving this problem. Second report. This work represents a significant advance and demonstrates for this first time the microporosity which can be induced in the open framework metal organics. Third review. I agree with the authors when they state that the establishment of porosity in the open metal organic frameworks is important. This has been and continues to be a concern in publications involving this class of materials. In that regard, I find this paper refreshing. So, okay, you can make, because of those strong bonds, you can make architecturally robust materials, and now we're off to the races. The next experiment, so far, nobody paid any attention in the community. Okay, except when we made MOF5. And MOF5, the reason everybody paid attention is that, one, is that it's extremely beautiful compound. And Michael O'Keefe put the yellow ball inside. The yellow ball initially was red and blue and pink, and Hallian would complain that those colors are just too ugly. In the end, we use the yellow ball because ASU, in their logo, they have a nice yellow sun. And so we put it in there to indicate the space within which one can incorporate other molecules. There are these rooms in the hotel that Olaf referred to. The reason people paid attention to this one is that not only was it architecturally robust, but it gave an extremely high surface area, almost 6 times the previous record, which of course was terrifying to me as an assistant professor, breaking the record of porosity in an area that has, as Susumu said, is more than 1,000 years old. So this was very exciting because it meant that we can now take inorganic chemistry and organic chemistry, 2 fields that are practiced separately and taught separately. We can combine them into materials that encompass space and lots of space, and, well, so much space that in a gram of material, which is no larger than a sugar cube, you have space that is as much as an entire football field. Okay, and the reason this is exciting is that BASF, with Ulrich Müller, that I will present shortly, we showed that, in fact, if you zoom in on one granule of this solid, as we are doing here for the MOF5 crystals, you see that the pores have no walls. It's a scaffolding, and which is the arrangement where you maximally expose the interior of the structure. That's why they have extremely high surface area. In many ways, we've exposed every atom in the structure and made it a surface onto which hydrogen or carbon dioxide could bind. That's why they have such high surface area. So with that in mind, now we can look at hydrogen storage, which we did, carbon capture, and show that, in fact, with carbon capture, this is actually an old paper, but in a tank filled with MOF, you can store 18 times the amount of carbon dioxide when the MOF is in the vessel. And then with BASF, we developed a methane natural gas tank where you take the regular fuel tank and you stuff it with MOF, with no other change to the engine, and this car can drive 3 times the distance because of the MOF is compressing the gas inside its pores compared to a tank that does not have the MOF. And this automobile was driven all over the world to show that, in fact, the natural gas that's being supplied in the various locales around the world, with whatever contamination might be in there, that the MOF can survive that journey, and it did. And so this was really an amazing illustration of the power of MOFs. We also, very early on, showed that, in fact, you can use the MOFs to bind toxic gases. And more recently, you can take nerve gas, put it in a MOF, break specific bonds, so the MOF acting as a catalyst, specific bonds in that nerve gas, and make it from a harmful molecule into a harmless molecule. So you can see how exciting everything has been, and more exciting than everything that I just said is we did the impossible in chemistry, which was that you could take a solid and at will customize the interior of that solid by virtue of the chemical functionality that decorated the interior. And so this immediately led us to realize that they would have endless applications. And not only can you functionalize the interior, but you could expand the pores by virtue of lengthening the linker. Now that of course, that was obvious. Getting it to work is the real accomplishment, I think, here. I think ideas are, in some respects in this field, ideas are cheap. I think trying to get those ideas to work is the real challenge. And I credit my students for all the innovation that has come out of the group in that regard. So you can see that the Nobel Prize Chemistry Committee was brilliant in describing the MOF field as that we have created rooms for chemistry where molecules can play in those rooms. They can be transformed, they can be trapped and released and so on. Then two collaborators that have worked with me for a long time, Michael O'Keefe and Davide Proserpio, took something that A.F. Wells, long time ago in his textbook, outlined the power of the node and linker approach that we've been talking about, and showed how that can be applied to crystal structures, not necessarily porous materials, but crystal structures in general. This approach was elaborated by Michael O'Keefe and Davide Proserpio to the point of developing really a kind of theory as to what building units, when they combine, what these building units could assemble into. You can see here different shaped building units and the kind of networks that they would produce. And this became then sort of a theoretical backbone for the field. Now you can see that some of these shapes have not quite been done, but I think, Mohammed, you probably filled in already some of these boxes. So then Ulrich Müller attends one of my German zeolite conferences where I was talking about MOFs. And he told me that the surface area number that I shared with you was so unbelievably high that I thought it had to be a misprint. Okay? And he proceeded to, at BASF, to try to reproduce our data. And thankfully, it was very reproducible. In fact, the way we describe, if you look at that paper, the way we describe the synthesis can be reproduced by a high school student, because we were focused on a lot of detail in describing details in that synthesis, and that started a long-term collaboration with BASF. Needless to say, they funded my research significantly over the years and given me tremendous freedom to do whatever I want scientifically with those funds. And very quickly, we together successfully started scaling up MOFs to multi-ton quantities, and this then became an important contribution to the MOF that is already deployed in Canada to trap CO2 from cement plants. Cement plants emit almost 1/3 of the total industrial emission of CO2. So they're big emitters. And so now, with this contribution, BASF is already scaling up this MOF to hundreds of tons. And it is deployed now in at least 3 cement plants, and it's capturing the CO2 from flue gas before it reaches the atmosphere. So I think that MOFs have entered the societal stage. I think that we will see many, many more applications. On a basic science level, the future, I think part of the future of MOFs is in what I call multivariate MOFs. MOFs where the skeleton that I've been describing remains ordered and regular, but the interior has functional groups that are covalently bound to that skeleton. And you could have many of these groups, many different groups, functionalizing the interior so that you have a heterogeneous interior trapped within the order of the skeleton. This heterogeneity within order is so useful that, in fact, we demonstrated that this MOF could have many different amino acids covalently bound into the walls, arranged in a random fashion, that some of the environments within this multivariate MOF code for breaking the same bond that an enzyme TEV protease can do. That's almost like a miracle. You have got an enzyme that evolved over millions of years, programmed to just break one amide bond among many amide bonds. And now you have a MOF where you threw in amino acids bound covalently to the walls that has some microenvironments that code for the same selectivity as the enzyme. I think that's the power of MOFs. This idea of heterogeneity, which pervades biology, now can be trapped inside the homogeneity of the MOF skeleton, and you can achieve what enzymes do, except now on a much wider set of conditions than enzymes operate on. So that's, I would say that needs further development. Okay, we don't have techniques to characterize what the sequence of these amino acids or these functionalities are in the pores, so techniques need to be developed to figure out how do these multivariate structures operate. But I think the driving force here is that in this and other studies that we've done, these multivariate structures do a lot better than the components or the sum of the components. And I think that's going to be a driving force for many of us to continue to work on them and characterize them. Another area that I'm very excited about is what I call ametry. Ametry is an emerging field that crosses AI with materials and chemistry. And it is the science of using AI for the design and synthesis of materials and for connecting chemical structures to properties and vice versa. Properties to structures, structures to properties. So I'll give you an example of what we've been doing. We've been doing a lot in this area for the last 3 years. I've intensified our efforts in using LLMs and machine learning algorithms to try to transform this chemistry into a more, let's say, modern chemistry. So we use ChatGPT here with Zach's help. He's in the audience here, he's a professor now at WashU, to edit the linker, one of the linkers that is so important in water harvesting. So here's an example of a water harvesting MOF. It's called MOF 303. It's made from zinc oxide rods that are going in and out of the screen and linked together by a small organic linker called perazolate. And we've characterized this with single crystal X-ray diffraction. So this is not just an artist's rendering of the structure, but rather it comes from real data on the positions of the atoms. Okay, and I'm going to slice out one of the pores to show you where each water molecule, again, each water molecule was characterized by single crystal X-ray to show exactly where each water molecule sits and study the binding sites of water. So what you see is that the first water molecules obviously go to the most hydrophilic sites, water-loving sites. And then once those sites are filled, they bridge over what is a hydrophobic sites, okay? So you can see that in the interior of the structure, if I was a water molecule floating inside the pore of the structure, I'll see a grid around me of hydrophilic and hydrophobic, hydrophilic, hydrophobic. And this water-loving and water-hating regions allow you, this push-pull, allow you to control how tightly water is bound in the pores, and therefore at what temperature I can remove the water so that I can harvest it and drink it. Okay, and that turns out to be temperature of about 45 degrees C or 50 degrees C, okay, which then was so exciting that the students went to Death Valley to show that, in fact, this MOF could be used to harvest water in the driest of deserts. And you can see here they have made pancakes of the MOF, put it in the device, and during the night, you expose this to the atmosphere. Water in the atmosphere goes inside the MOF, and when the pores are filled, as I showed you from the previous slide, during the day when it gets hotter, the device heats up and you can harvest water with no energy input aside from ambient sunlight. And the water that you harvest is ultra pure. There's no metals in it, no organics, no contamination. The MOF itself is really a water filter. And so there are, some of you may have seen pictures of my students drinking this water. So this is nice, and we can make it nicer with ChatGPT. So you ask ChatGPT, I have this MOF, and it has this kind of linker, make me a better linker that's going to give me more water, and it starts putting different atoms around the central ring and playing with the linker. And it also gives you the conditions under which to make that MOF. So Zach can teach ChatGPT to understand what a MOF chemist understands, and it can spit out the conditions under which to make all these MOF, which it did, and we and Zach went ahead and made those compounds and measured their water adsorption behavior. And it turns out that some of these MOFs that came out of ChatGPT are the best MOFs for water harvesting. And some of them give you more than 50% water above and beyond what I showed you with MOF 303. Okay, and that's not significant because, I should say that's significant, or that's not insignificant, because that's 50% more water every cycle. Every cycle that you do, every day for 7 years. Okay, and that is so exciting, because now it's almost in society. Now we have devices that deliver almost 2,000 liters per day, the most energy efficient devices for water harvesting, every day for almost 7 years. And at the end of the MOF journey, you can separate the metal from the organic and reassemble it in water using zero discharge methods. So it's completely cyclable. And here again, with no energy input, just ambient sunlight or low-grade heat, waste heat, you can get almost 850 liters per day, every day for 6 to 7 years. And so, finally, I have two more slides. Okay. So, this molecule to society, why not we build an AI platform that allows us to do everything that I just described to you, but using AI much faster, double the number of discoveries, connect the molecule to the material and the material to the device, and the device operating mechanically and in terms of mass transport, energy transport, efficiently and very quickly. So we have a theoretical cycle, an experimental cycle that feeds into the theory cycle with negative results and positive results, and we have a scaling cycle. And my last scientific slide is I just want to show you that just using those two cycles, with 2,600 reactions, we are able to invent double the number of ZIFs, this is a subclass of MOFs, that my group has done for a long time. So a student using these adaptive machine learning algorithms that we put in and made them chemistry friendly, double the rate of discovery compared to the students that are not using the machine learning algorithms. Okay, so that's the journey that allowed us to have MOF chemistry go from molecule to society, and that's what you see happening today. So I want to acknowledge my former graduate students. A lot of them are here in the audience, and I want to say thank you for failing and failing and failing so that you can succeed. You have truly inspired me over the years. And visiting scholars, senior and junior. And I also want to acknowledge some special people that you meet along your life's journey. And they're very special because they give you extra support and extra love beyond what is ordinary. And these are some family and friends who have been with me over the years and cared a lot about me and my success. Thank you very much. And my current group members, I want to thank the Academy for making them happy, happier, And the funding agencies that have stayed with me, I want to acknowledge BASF and Saudi CACS for giving me money that I can use unconditionally. And I want to thank you for your attention.
Thank you. Thank you. Thank you so much, Omar, for that very inspiring and visionary talk. Thank you so much. This concludes the Nobel Lectures in Chemistry, but before we finish, I will now invite all the laureates to come up on stage. You should go in there. Yes.